Okay, so in this video, we're just going to quickly go through some examples that were not in the last video. Um, I'm going to do this on a separate slide just so I have more space to write. And so please make sure that you either have this on another tab or something so you can easily go back and forth. But the question, I'll go ahead and read the question, then I'll switch to a different window. The question says a 0.55 kilogram mass is attached to the end of a horizontal spring. The spring constant of the spring has a magnitude of 15 newtons per meter. The spring is initially pulled out 5 centimeters from equilibrium and then released from rest at time t equals 0. Okay, now the first question, which I'll call question A, says calculate the period of the mass on the spring. Okay, so just to go back to this, the period of a mass on a spring is given by the equation T equals 2 pi times the square root of m over k. Okay, and I kind of showed you where that equation came from in the last video, going over the notes, and we also saw the same equation that Walter Lewin wrote down in the video from our last class. Okay, and so as long as we have the mass and we have the spring constant, this is a very easy calculation to do. That's just going to be 2 times pi times the square root of the mass, which here is 0.55, divided by the spring constant, which is 15. Okay, in your calculator, keep in mind that the square root is over the m and the k, and so what you want to do is you want to do m divided by k and then make sure to square root that number. So I'm doing 0.55 divided by 15. I'm going to square root that number, multiply by 2, multiply by pi. Okay, and so if you do that correctly, you should get the period is equal to 1.203 seconds. Now remember, the period is the time it takes to go back and forth one time. Okay, it's the time for one complete cycle. So the period is not going to change even as it goes back and forth, back and forth, back and forth, because there's no friction in the system. Okay, so the period is a set number. Don't confuse big T, which is period, with lowercase t, which can be any value of time. Okay, so the period is one specific time. Now, question B says, determine the frequency of the mass in hertz. Okay, so frequency is the reciprocal of period. Okay, and it says this if you go back and look in the notes, but frequency is 1 divided by the period. And so if we do 1 divided by the answer that we just got, then we get 0.831 hertz. So the unit for frequency is hertz. The what you write for hertz is capital H, lowercase z, but the word hertz is Hertz. It's named after a guy, a physicist. And what hertz or what frequency represents is frequency tells you basically how many times does it go back and forth per second. Okay, so period is the time for one complete cycle, whereas frequency is basically how many cycles do you have per second. Okay, not to be confused with angular frequency. Remember, angular frequency is 2 pi times the frequency, and angular frequency is omega. So make sure you don't mix up frequency with angular frequency. Okay, so going to the next question, it says, how do your answers to the previous questions change if the spring was originally pulled out to 10 centimeters instead of 5 centimeters from equilibrium? Okay, so I don't have really much to write down here. If we change the amplitude, so basically what's happening here is the amplitude is originally 5 centimeters. The mass is pulled out to 5 centimeters and let go, so the amplitude is 5 centimeters. And so the question is basically asking what would happen to the period and the frequency if you double the amplitude. And the answer is nothing would change. If you look at the equation for the period, we have 2 pi times the square root of m over k. Nothing in the equation tells us anything about amplitude. And so what that means is amplitude is not a factor that affects period. So in other words, even if the amplitude is doubled, it's still going to take the same amount of time to go back and forth one time, which is a little counterintuitive. You might think like if you pull it back farther, it's going to take longer to travel all the way there and back. But remember that when you pull it back farther, the force from the spring also increases proportionally to the displacement. And so even if you pull it twice as far, the force doubles. And so everything, all of the math works out so that it ends up taking the same amount of time, even if it has a farther distance to travel. Okay, so nothing changes by changing the amplitude. Amplitude does not affect the period of oscillation. Okay, at least in true simple harmonic motion, it doesn't. Now, for a simple pendulum, like we talked about in the last video, a simple pendulum is not truly simple harmonic motion because you have to use a small angle approximation to make it into simple harmonic motion. And so, as you'll see, as you'll be investigating in the lab you'll be kind of testing, does the amplitude affect the period? It shouldn't. If it was truly a simple harmonic motion, the amplitude shouldn't affect the period. And so that's something you'll have to test in the lab with a pendulum. Okay, but for the mass on the spring without any friction or resistance, it is truly simple harmonic motion, and so nothing would change here. Okay, so question 4, it says determine the first time t1 for which the mass has a position of x equals 2 centimeters. Okay, so I want to find the time t1 where x is equal to 2 centimeters. Okay, so I know that the equation of motion for simple harmonic motion looks like this. It's a times cosine omega t plus phi. Okay, in this specific example, I know that x is equal to, the amplitude is 5 centimeters, and I know omega, or at least I can find omega, because remember, omega is 2 pi divided by the period, or 2 pi times the frequency. And so using this equation here, I can calculate the angular frequency just by taking the frequency which I found for part B and multiplying by 2 pi. So in other words, 2 times pi times 0.831 gives me an omega of approximately 5.22. Okay, so in the parentheses here, I have 5.22 times t, okay, and then phi is equal to 0. Okay, and so for part D, I want to find the value of t such that x is equal to 2 centimeters. Okay, so I'm looking for the first time, which in the question it calls t1. I'm looking for a time t1 where this equation is satisfied. Now, the reason it says the first time is because an object in simple harmonic motion is going to go back and forth, back and forth, back and forth, an infinite number of times because there's no friction. And so theoretically, there's an infinite number of possible answers where x is going to be equal to 2. This is why in the question it says the first time t1. Okay, because with the cosine, the sine function, it repeats every 2 pi radians, and so that's why you have an infinite number of possible values of t. Okay, so for the first time though, I can just solve here for t1. So I divide both sides by 5. That gives me 0.4 equals cosine of 5.22 t1. Okay, to get t by itself, it's inside a cosine, so I need to do inverse cosine on both sides. I do inverse cosine of 0.4 is equal to 5.22 times t1. And then finally, to get t1 by itself, I just need to divide both sides by cosine of 0.4. Please make sure that when you're doing this, by the way, make sure that your calculator is in radian mode. Okay, so inverse cosine of 0.4, okay, divide by 5.22 gives me a time of 0.222 seconds. Okay, and so that's how long it takes to go from 5 centimeters to a positive 2 centimeters. Okay, so this is questions A, B, C, and D. Now, I do need more space to finish out the question, so pause it there and rewind the video if you need to go back over any of those past questions, but otherwise I'm going to erase. Okay, so just to give myself some space, I'm going to erase up here. And then I'm going to take a look at the next question, which is question E. Okay, so question E says, determine the time t2 for which the mass has a position of x equals -5 centimeters. Okay, so in other words, at what time, let me just erase everything so we can see everything. At what time t2 does the mass have a position of x equals -5 centimeters? So there's a few different ways we can approach this question. The most straightforward way to do E is basically just to do the exact same process that we did for the last question. Okay, but instead of putting 2 here, we would put -5 in for x. Okay, so -5 equals 5 times cosine omega t. Okay, so we have omega, we have t2. Okay, and then we divide both sides by 5. We do inverse cosine, and we solve for t2. Okay, and there's nothing wrong with doing that approach, but if you take a minute to actually think about what's happening in the situation, there's actually an easier way to do this question. And so just to remind you, the period that we found at the beginning for the very first question was 1.203 seconds. Okay, that was the answer for the first question. If you read the question, it's basically asking how long does it take to go from 5 centimeters to -5 centimeters. Okay, but going from 5 to -5, that's half of a period. Right? So one full period would be to go from 5 to -5 and then back to 5, right? That would be one cycle. This is half of a cycle, okay? Going from 5 to -5, that's half of a cycle. And so the time, t2, would just be half of the period. And so all we need to do is take the period that we already have and divide that by 2. And of course, the answer there would be 0.6 seconds. Okay, and if you did it the other way with the inverse cosine and all that stuff, you would end up basically getting the same answer that way. Okay, and so a lot of the time, pause and think about what you're doing before you do too much complicated math, especially if it's on like the exam or something. Okay, so that's question E. And then for the last question, it says calculate the maximum velocity that the mass can reach during the oscillation. Okay, and so just to remind you, let me just erase. Okay, so this is going to be the last question, which is F. Okay, so just to remind everybody that for an object in simple harmonic motion, V max is equal to A times omega. Okay, well, we have A because it's 5 centimeters, and we have omega because we found it before, it's 5.22. And so if we just do, A times omega, we do 5 times 5.22, we get 26.1, and that's going to be centimeters per second. Okay, so that's going to be V max. Now, of course, that's not in SI units. You always want to end up with in the units with whatever the question tells you to do. Obviously, if we wanted to convert to meters per second, we would divide that by 100. Okay, but that is the answer to the last question on this slide. Okay, so pause there if you need to look at E or F some more. Okay, so let's take a look at just a few more questions. Okay, so this is kind of a more conceptual question. In fact, I kind of want you to pause the video here and try to answer this question on your own, and then we'll talk about it in just a second. Okay, so pause and answer this question on your own. Okay, so here's what this question says. It says, when an object oscillating in simple harmonic motion is at its maximum displacement from the equilibrium position, which of the following is true of the values of the speed and the magnitude of the restoring force? Okay, so maximum displacement basically means you're at the endpoints. Okay, so the displacement is equal to the amplitude and you're at the endpoints. But one of the things we've talked about previously is that at the endpoints, the object stops moving because it has to stop and then change direction. And so at the endpoints, the speed has to be 0. Based off of that fact, you can eliminate 1, 2, and 4. Okay, the restoring force, the force and the acceleration are proportional to each other. Okay, so think about what's happening to the acceleration. If the displacement is at a maximum, the acceleration is also at a maximum. Okay, now how would you know that? Because the very definition that we started with is that in order for an object to move in simple harmonic motion, it has to be proportional. The acceleration must be proportional to the displacement. So in other words, wherever x is 0, a is 0. Wherever x is at a maximum, a is at a maximum. Okay, and if whatever's happening to a is also happening to the force as well because of Newton's second law. Okay, so at maximum displacement, the acceleration is at a maximum. That means the restoring force is also at a maximum. So the answer to the question is 5. Okay, so pause it or rewind if you need me to go over that again. And let's take a look at one or two more examples. Okay, so this is kind of a tricky question from the quest homework. So if you want to pull up the quest, now's the time to do it. But let's take a look at this question. The question says a particle executes simple harmonic motion with an amplitude of 1.24 centimeters. At what positive displacement from the midpoint of its motion does its speed equal 1/2 of its maximum speed? Okay, so first of all, we obviously have the amplitude as given, okay, but we don't have a lot of other information. Now the question says at what maximum displacement from the midpoint of the motion? So the midpoint of the motion is equilibrium. So displacement from equilibrium is x. So basically our goal is to find some value of x, and at that value of x, the speed there, okay, remember we're talking about v, the speed or velocity, has to be equal to half of the maximum speed, and we want the answer in centimeters. Okay, so make sure you have this question up in a different tab or something. I'm going to switch to different windows so you're not going to be able to see the question. Okay, so let's pull this over to where I have more space to write. So the amplitude is 1.24 centimeters. Okay, and I'm just going to write out some stuff that I know has to be true. Anytime you're doing a question in physics that you don't really know how to do, it's always safe to start with what do you know has to be true. Now, I know, first of all, I know that Vmax is equal to A times omega. Okay, we talked about that in the last video. The question is asking me for the value of x at half of the maximum speed. Okay, so what is half of the maximum speed? What is v at that moment? Well, half of the maximum speed would just be a times omega divided by 2. Okay, so in other words, this is the value of v at which I want to find the value of x. Okay, when so at this value or at this moment of time, the speed is equal to a omega divided by 2, so half of the maximum speed. Okay, and so you're not given a lot of information here, and so this is kind of a tricky question. The correct way to do this question is to use conservation of energy. Okay, anytime you ever have any type of simple harmonic motion, you always can use conservation of energy. And basically with conservation of energy, you know that the kinetic energy and the potential energy, that sum always has to be equal to a constant. Okay, so imagine this object in simple harmonic motion is at the endpoint. Okay, let's just say it starts at the endpoint. What is the total energy? Okay, well, the total energy at the endpoint, it's not moving. The speed is 0, so there's no kinetic energy. And so the only type of energy there is potential energy, specifically spring potential energy, which would be 1/2 kx squared. But remember in this situation, x at the endpoint is the amplitude. Okay, so we have 1/2 ka squared, and that is the total energy of the system. Okay, it can never have any more or less energy than that. Okay, now at any other moment in time besides the endpoint, the total energy is always going to be equal to the kinetic energy plus the potential energy, right? Okay, because energy is conserved, these two things have to be equal to each other. In other words, 1/2 ka squared has to equal 1/2 kx squared plus 1/2 mv squared. And remember, my goal is to find a specific value of x. Okay, I have the amplitude. I don't have a mass. I don't have a spring constant, but I do suspect they're going to cancel out since it's not given in the question. All I know from the question is that the amplitude is 1.24 centimeters. Okay, so from the equation, we see 1/2 cancels out. And at this point, it might look like we're stuck, but remember that v, the specific v I'm trying to find, is this v right here, okay? And so if I take this v and plug it in to the equation down here, then remember v squared would be a squared times omega squared divided by 4, because if you square v, you have to square every single term in here. And so if you make the substitution into the equation, we have k a squared equals k x squared plus m times um, a squared omega squared divided by 4. But remember, for mass on the spring, omega is equal to k over m. Okay, and so if I make that replacement, you can see what happens here in just a second. Okay, so I have m, so this is omega squared is equal to k over m. I have a squared divided by 4, and then I can replace the omega squared with k divided by m. The m's cancel, and now that I have a k on top, the k also cancels. Okay, and so I end up with the equation a squared equals x squared plus a squared divided by 4. Okay, I introduce a common denominator, which is 4. I subtract the a's to the same side, so I get 3a squared divided by 4 is equal to x squared. And then I just do square root on both sides. Okay, and so if you plug in a, 1.24 squared times 3 divided by 4, square root that number, and you get 1.074 centimeters. Now, I did not convert to meters, but that's only because the question actually asked for the answer in centimeters. Okay, so that is kind of a challenging question because you have to know to apply conservation of energy. But once you figure that out, it's not too bad. Okay, so pause it there if you need to look at that some more. Okay, so that's actually the last example we're going to do in this video. We can talk about this example at another time. The last thing I do want to tell you is that I'm going to put a link in the instructions for today for you to watch a clip of Walter Lewin swing on a pendulum. And the main takeaway that you'll see in the video is that the mass of the pendulum actually does not affect the period of oscillation, and you'll see that demonstrated in a very visual way. Okay, so as always, if you have any questions, please let me know or please rewatch the video. Otherwise, I will see you next class where we will be doing our Lab 7 involving pendulums. Okay, have a great day.